Hello there, this is True Socrates. Welcome to video number 26 for multivariable calculus, known as Math 5C at Pasadena City College. So in our last two videos, we talked about space curves and tangent vectors to these space curves, and we also saw how to draw them in GeoGebra using the curve command. So we need these curves because those are going to be the domains for the integral that we are going to construct today. So the name of the chapter is about contour integrals and vector fields. So we will today construct the contour integral of a scalar function. In our next video, we will look at the vector fields, and that will sort of complete our picture. So I will see you on page 212. All right, so let's start with notation. How do we write a contour integral for a scalar function? All right, so it's going to look like this. We just came from triple integrals, right? And now we're back to a single integral. And instead of a to b, we're going to write c to denote the curve, which will be our domain. And we will have a function of two variables or of three variables, all right? And either way, we'll have this ds, where that's the lowercase letter s. In the next chapter, that's going to turn into an uppercase capital S. Okay, so to generalize, we will just write it simply as integral along c of f ds. Okay, so in the first integral, though, c is only in x and y, so it's a plane curve. And in the second case, c can be a space curve. Okay, it can have all of x, y, and z. So here are possible parametrizations for these curves. Okay, as usual, we will have x and y as functions of t, or x, y, and z as functions of t, where t is from a closed interval from a to b. Okay, so we're not going to look at infinite lines or infinite helices, plural for helix. We're going to bound the domain to be a closed interval. All right, so C is our domain, and of course our functions are assumed to be continuous functions on the curve. That means that we need them to be continuous on an open set which just is slightly bigger than our curve. Okay, so what does this contour integral mean? Okay, well, the first step is just like how we create the definite integral from a to b of a function in one variable. Okay, so our domain is t from a to b. We will partition, once again, a to b into n subintervals. All right, so the width now is called delta t. And of course, it is b minus a, the length of the interval, divided by the number of subintervals we want to divide it into. Okay, so just like way back in chapter 2, this partitions our interval into subintervals, and the endpoints are a, which we will call t sub 0, and then t1, t2, you move to the right by delta t, hopping along each time until you get to the right endpoint, which we will call t sub n. It's going to be b. Okay, so of course every subinterval has the same length, delta t. Okay, but now t is the domain for our curve c. All right, so how do these partitions affect c? Okay, well, these points correspond to a point on the curve. So on the subinterval from ti minus 1 to ti, the left endpoint will become the point r of ti minus 1 on the curve, and the right endpoint will correspond to the point r of t sub I on the curve. Okay, so we're going to have a subcurve, which we will call ci, or a subarc. And just like in the definite integral, we will now choose a representative point. Okay, so pick a point somewhere between ti minus 1 and ti. Call that point ti star. Okay, can it be the midpoint? Sure. Left endpoint, right endpoint, and so on. Okay, but in a minute, we're going to find out that there's actually a good or a logical choice for this ti star that is better than other choices. All right, so corresponding to this representative point ti star, we'll have a point on the actual subcurve, and that's going to be r of ti star. Just plug in ti star into x, y, and z in our parametrization. Okay, let's look at the picture. Ta-da! Okay, so for brevity, we will call this point f of r of ti star, okay, which looks like a strange notation. But after all, this represents a vector, and the endpoint of that vector represents a point on either the plane or in space in this case. Okay, so that's just shorthand notation for this much longer thing. Okay, so here's a picture of what we've done so far. All right, so here's the interval from A to B. I subdivided it into 6 parts. 1, 2, 3, 4, 5, 6, 7. Just kidding. And at 6. Okay, so that corresponds to 7 points. Okay, because you start counting at 0. So here is the left endpoint, the point on the curve corresponding to the left endpoint A, T0, T1, T2, T3, T4, T5, T6, which is our B. Okay, so you're kind of looping around this curve. Ta-da! Okay, so what we're going to do is we're going to zoom in on one of the subarcs. Okay, so here's what it might look like. All right, so the left endpoint ti minus 1 corresponds to this point, and the right endpoint corresponds to this point. Okay, the representative point is somewhere in between. Okay, so we're going to plug in that representative point into our function. Okay, just like we did for the definite integral. We have our f of xi star, something like that. Okay, so we are just missing one more ingredient before we can create the contour integral. And that is, well, how long is this subcurve? Okay, so yeah, it's not a straight line segment, but if your delta t is small enough, we could approximate it with the direct line segment from this point to that point. Okay. Oh, but wait a minute. We know about vectors. Okay. And that is why vectors are so useful. This point corresponds to a vector. This point corresponds to another vector. The vector where we take the difference between this vector and that vector represents the vector from this corner to that corner. Aha! Okay, so the length of this subarc, which we will denote as the length of ci, okay, pronounced the same way as you would the length of a vector, would be the length of r of ti minus r of ti minus 1. Okay, and now we're going to do something clever. We are going to multiply and divide this by delta t. Okay, so why is this something good? Why is this clever? Well, we just talked about the derivative of a parametric curve, right? And as you recall, this appears in the formula for that derivative where delta t goes to 0. But wait, we are subdividing this curve into several pieces. And of course, we want the number of pieces to go to infinity. When that happens, delta t goes to 0. Okay, so therefore, as the number of pieces goes to infinity, then this difference quotient, okay, approaches the tangent vector. And to be consistent, let us use our left endpoint corresponding to ti minus 1 as the root of our tangent vector. Okay, so there we go. The length of this subarc is what we have over here, and that is approximately the magnitude of the derivative of the parametric curve evaluated at the left endpoint ti minus 1. Okay, so therefore, to be consistent, we might as well also choose as our representative point ti star the same point that we chose over here, which is ti minus 1. All right, so great. We are now ready to create the contour integral. Okay, so here's our definition. The contour integral along C of f of x, y, z ds is the limit as the number of partitions n goes to infinity of the Riemann sum, I from 1 to n, of f evaluated at the representative point r of ti star times the magnitude of the derivative r prime evaluated at ti minus 1 times delta t. Okay, and we said let us choose as our ti star the left endpoint ti minus 1 so that these two are exactly the same. Okay, so based on the definition of the definite integral way back in chapter 2, we can write this as the definite integral from a to b of f of r of t times the magnitude of the derivative r prime at t dt. Okay, so before we actually do an example and compute a contour integral, we are going to restrict the kind of curves that we will integrate on. Okay, now why is that necessary? It's because of this pesky thing, this magnitude of r prime of t. Okay, we don't want that magnitude to be 0, otherwise the function gets killed. Okay, so we want the function to survive, right? So what we're going to do is we want our curves C to be what are called smooth curves. Okay, so it basically means that the derivative is always defined, okay, and it is never the 0 vector, right? So we call r of t a smooth parametrization for C. Okay, so we will also say that r of t produces a smooth curve C if r prime satisfies these two conditions. Right, so with that restriction, the magnitude of your derivative will always be positive, and so your integrand will be prevented from becoming 0, unless the function itself is 0, and there's nothing wrong with that. Okay, so let's take a look at what smooth curves look like versus non-smooth curves. Okay, start with lines. Okay, we saw that the derivative of a standard parametrization for a line is just a direction vector, and we don't allow the direction vector to be 0. Okay, so therefore, that gives us a smooth curve. Okay, how about our standard helix? Okay, so the derivative is negative sine, positive cosine, and 1. Oh, 1. So as soon as one of the coordinates is non-zero, okay, a non-zero constant in this case, then your derivative can never be the 0 vector. Okay, excellent. Now, we're going to need, as we can see over here, the length of r prime of t. So let's practice on that. Okay, here's r prime, square, 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 add it all together. Oh, sine squared plus cosine squared, that's just 1. So we get 1 plus 1, square root of 2. Okay. In the first section of this chapter, we saw non-circular helices, elliptic helices. And let's see what happens if we find the length of the tangent vector for these elliptic helices. Okay, so here's one for example. You got a 3 here for cosine and a 4 for sine. They're not the same. Okay, so take the derivative, minus 3 sine, 1/2, 4 cosine, and then let's take a look at the length and what's going to happen. Oh, so 3 becomes 9 sine squared, 4 becomes 16 cosine squared. That's just a constant. Okay, but oh yuck, 9 sine squared, 16 cosine squared. That does not add up to 1 this time. Okay, so maybe the best that we can do is we can borrow a 9 from the 16. You got too many anyway. So those 9 cosine squares and 9 sine squares, those combine to 1. Okay, 1/4 stays the same. You're left over with 7 cosine squared. And unfortunately, this ugly thing does not simplify. Okay, so for now, we are going to ignore elliptic helices when we look at the contour integral of a scalar function. Okay, when we do contour integrals for vector fields, okay, coming soon in a couple of videos, then we can bring them back, okay, because something nice is going to happen. All right, so here's an example of a parametric curve, which is not going to be smooth, okay, and it looks very innocent. T squared plus 4, t cubed minus 2, negative t squared plus 1. What could possibly go wrong? We love polynomials, right? That's just a polynomial. Okay, we can still find the derivative. You'll get 2t, 3t squared, negative 2t. So it always exists, okay? However, if you plug in t equals 0, everything is going to be 0. So the tangent vector for t equals 0 is a 0 vector. This is not a smooth curve, and this is how it looks like if you plot it in GeoGebra. And yeah, that thing looks like a corner or a cusp, okay? So that is not the kind of function that we like in basic calculus. We won't like it either for our contour integrals, okay? So we will provide you with curves where this does not happen, okay? If life gives you a curve like this, all you have to do is break it up, okay? So if this is the domain of a contour integral and you really have to compute it, just break it up into one contour integral followed by another contour integral, okay? Just like we do in calculus when you have a function which is not continuous at a point somewhere in your interval. All right, so let's go back then to our main topic. How can we set up and compute a contour integral of a scalar function? Okay, several steps. Well, first you need a smooth parametrization of the domain. Okay, so you have either x t y t or x t y t z t, and you need to know the domain. All right, we will plug in that parametrization into the function, whether it's in 2 variables or 3 variables. Then we will compute r prime, okay? Because remember, we need the length of r prime. While we're at it, we will make sure that it is never the 0 vector. Okay, so yeah, it's this pesky square root that's going to give us a problem. So we're only going to give you curves where you can simplify the radical, or maybe the function that goes with it is going to cooperate, shall we say, so that you can perform the integral, let's say maybe by substitution or maybe integration by parts, okay? So multiply those two together, and then we will integrate from A to B. Okay, yeah, once you set it up, it's usually downhill from there, back to single variable calculus and knowing your integration techniques, okay? So this is what I was saying a minute ago. If you are not given a smooth curve, then hopefully we will have what is called a piecewise smooth curve, where you have several curves literally connected together so that each curve is smooth, but maybe at the connecting points, you don't have a derivative or your derivative is 0, okay? In which case the contour integral is just the sum of the integral of the same function over the component curves. Okay, so let us take a look at an example. Oops, I lied. Before we look at the example, we're going to talk about, well, what does it mean? Okay, how do we interpret this contour integral? Okay, well, once again, density functions come to the rescue. Okay, so what does it mean in this case for a curve? Okay, so we can think of a curve like a helix as a piece of wire, okay, and we have our representative point, correct, ti star, okay, and well, what can we do? Okay, so imagine that you have these very fine wire cutters and you snip a little portion of that wire, okay, and then you take that piece of wire and you weigh it on a very sensitive scale. Okay, now take the limit as the length of that wire goes to 0. Okay, the ratio of the mass of that piece of wire to its length is what we can define as the density of that piece of wire at that point. Okay? So of course, this goes backwards. If you want the mass of that piece of wire, that subarc, you can take the density multiplied by the length of that subarc. Okay? So here is our formula. Okay, the mass is the density times the length. Oh, but wait a minute, isn't that the magnitude of Ri at Ti star? Okay, Ri prime. Okay, so therefore, the contour integral of our density function along C gives us the mass of that wire. Okay, what happens if the density is simply 1? Well, what that means is that we are going to get the arc length of our piece of wire. Okay, of course, this interpretation works only if the wire does not cross itself. Okay, so in other words, our parametrization is a one-to-one function. Okay, so like the helix, for example. Okay, the helix does not cross itself, or a line segment. Okay, a line segment does not cross itself. All right, so here is our first problem. We have a piece of wire which is in the shape of a quarter circular helix. Okay, so here's a parametrization. I'm putting -5 sine t for x, 2t for y, 5 cosine t for z. Okay, so usually the cosine is on the x, the sine is on the y. Usually they're both positive coefficients. Let's play with them. Okay, so we can move the trig functions around, and we can have a negative coefficient as long as the absolute values are the same. -5 plus 5. They have to match. Okay, quarter helix, so our t will only go from 0 to pi over 2. Okay, we have a density function here, x squared plus 3y plus z. So yeah, x squared, why did I square it? Because that's going to be negative. Okay, we want a positive density. Okay, so we're going to square that. Y is safe because t is from 0 to 2, so I can do 3y. And z is also safe because between 0 and pi over 2, cosine is positive. Okay, so let's take a look at our helix and see that, yeah, this density makes sense. All right, I already input our helix into the curve command, -5 sine, 2t, 5 cosine. So there is our circular helix. Okay, so yes, the x coordinate is negative, okay, but the y coordinate is positive, and z is also positive. Okay, so it starts at 0, but it ends up at 5. Okay, so everywhere else in between, it's going to be positive. Okay, let's compute the contour integral. Ooh, we have 2 contour integrals. We need the arc length and we need the mass. Okay, so let's follow the recipe. Okay, so to prepare ourselves, let us plug in our parametrization into the function. Okay, so we're going to compute the density evaluated at r of t. Okay, so what does that mean? This is our density. We're going to plug x in our parametrization into x squared. Okay, so there it is. Y into 3y, 3 times y, z into z. Okay, there we go. So x, y, and z are now all gone. And what have we got? 25 sine squared of t, and then 6t, and then 5 cosine t. Okay, so that is part of our integrand. Okay, we're not yet ready. We still have to find the derivative. Okay, so we want r prime of t. Derivative -5 sine turns into -5 cosine. 2t turns into t. 5 cosine turns into -5 sine. Okay, Yeah, for a helix, it's a little bit forgiving. If you forget the signs, it's not the end of the world because we're going to square them anyway. So you just got lucky. If you forgot the plus or minus, we want the length. So we want the square root of the sums of the squares. So we got 25 cosine squared. And then we got 2 squared, 4, and 25 sine squared. Okay, so of course, cosine squared plus sine squared, we saw an earlier example, that just combines to 25, okay? So we get 25 plus 4, and of course, that is simply square root of 37, no, just kidding, 29. Okay, there we go. So that part of the integrand has a square root, but it's benign, okay, because it's just a constant. Okay, so yeah, how about the arc length, right? So let's find the arc length. Might as well get the whole thing for later. And so for the arc length, we got our domain is from 0 to pi over 2. So integral from 0 to pi over 2. And then we said, okay, bring this function in and multiply by magnitude of r prime, which is this, dt. Okay, that's our integral. Okay, so yeah, the setup is, of course, the crucial step in the process. And, of course, we can take that square root of 29 outside. Okay, so bring the rest here. And while we're at it, of course, we will need to turn sine squared into 1 minus cosine of 2t divided by 2. Okay, there we go. And yes. So not much we can simplify there, but that's okay. So we have 25 over 2. Turn that into fraction. Minus 25 over 2 cosine of 2t. And there we go. Okay, so all we have to do now is find the, oops, oh, I'm sorry, I'm so sorry. You're saying like, wait a minute, you're supposed to be doing the arc length. Okay, got excited there. Kidding. Okay, so here we go. We are finding the mass. Okay, so, yeah, what are the antiderivatives? Okay, bring the constant over. So we got 25 over 2t. And then we got, is that going to be minus? Yes, it's going to stay minus 25 over 4 sine 2t. Okay, it feels like we've done that like a million times already. So yeah, sine, cosine. Okay, and then 60 will turn into 3t squared. Don't use page down. And then we have sine, yeah, plus 5 sine of t. Okay, so we evaluate from 0 to pi over 2. Okay, so is that right? Everything good? Sine turns to cosine, 2 goes away. And that's 6t and 5 sine, yes. Okay, I think that's right. Shall we? So that's supposed to be the final answer. Okay, so what have we got here? 0, does everything go away? Yep, it's the cosine that trips you up, right? Cosine of 0 is not 0, it's 1. Isn't that annoying? So we have 25 pi over 2. 25 over 2 pi over 2. And then let's see, sine of pi is 0. Sine of 0 is 0. So that entire term goes away. T squared, so we got pi squared over 4. 3 pi squared over 4. Are we on the right track? It looks like we are. And lastly, sine of pi over 2 is 1. Sine of 0 is 0. So that is simply going to be 5. Yay! Yes, that looks like we have the right answer. Okay, so now the mass, which is of course a lot easier because for the mass, I'm sorry, the length. Why do I keep mixing them up? So the length will be integral from 0 to pi over 2 of just the magnitude of r prime. Okay, so it's just the square root of 29 dt. Okay, so of course that is simply square root of 29 times pi over 2. T becomes pi over 2. Okay, so square root of 29 pi over 2. All right, so that is our arc length and that is our mass. All right, so there's one more interpretation for a contour integral, and this is actually more visual. We can see the helix, the quarter helix, but we can't tell how heavy it is. We can't tell its mass just by looking at it. Okay, so something different happens if you have as your domain a plane curve, a curve on the xy plane, and your function in two variables is non-negative. Okay, so good things happen when things are positive or zero. Okay, in this case, the contour integral can be interpreted as an area. Okay, so just like the definite integral can be thought of as an area if our function is non-negative. Okay, why is that so? Because over xy, you are going to get the point xy, f of xy. Okay, so as you move along a curve, your height might change. Okay, and you won't be going necessarily along a straight line. When you look from above, you're just going to be on top of that curve. Okay, so as we do that, we form what you can think of as a curtain. Okay, and if we straighten out that curtain somehow, then the contour integral represents the surface area of that curtain. Okay, so that is going to be our second and final example. All right, so we want to find the surface area of the curtain formed by this function. We'll keep it simple, 2x plus y over 5, above the upper right quarter of this circle. Okay, so x minus 3 squared plus y minus 2 squared is 16. The center is at 3, 2, and the radius is 4. Okay, so first we're going to need to create, this time, a parametrization for this quarter circle because it is not given to us. All right, so I hope you remember how to do this. Okay, we're going to use sine and cosine. And let's keep in mind we want the upper right quarter of the circle. So it looks like our domain should again be from 0 to pi over 2. Okay, that's quarter of a circle. Okay, how do we make the rest though? Okay, so our center is at 3, 2. So those go into our x and y. Okay. But for x, we're going to use cosine. For y, sine. The radius is 4. So we have 3 plus 4 cosine of t and 2 plus 4 sine of t. Okay, our radius is 4. Okay, so we're going to go now to GeoGebra because what we're going to do is we're going to draw this curve on the xy plane. And we are going to draw the surface corresponding to this function when we restrict it to this quarter circle. Okay, so the domain is obviously all points xy on R2 on the xy plane, but we're restricting it to this quarter circle. Okay, so what we're going to get is a surface on top of this curve. Okay, so I hid our quarter helix and we will make our curve. Okay, so xy, z is 0, and our t is going from 0 to pi over 2. Okay, so we said that our x was, yes, 3 plus 4 cosine of t, and our y is 2 plus 4 sine of t, close. Aha! So there is our quarter circle, and again, it should be the upper right side. So yes, the complete circle should look like this. We only have the upper right side of that circle. Okay, so now how are we going to draw the curtain? So we are going to use the surface command. Okay, so how are we going to do it? X, Y, Z. Now we need two parameters. Okay, so our t is again going to go from 0 to pi over 2. Okay, and we're going to go from the xy plane up to our function, which is 2x plus y over 5. Okay, so remember the trick using vectors, we will use a v that goes from 0 to 1. Okay, so we've done that maybe a dozen times already, maybe not 1,000 times. Okay, so the x and y are exactly what we have over here, so maybe I'll just retype it. It freaks out a little bit when I do cut and paste. So annoying. Y, 2 plus 4 sine of t. Okay? So actually, if you are doing your homework and you're asked to draw the curve and the surface, you don't need to draw the curve separately, okay? Because the surface command will include that curve on the xy plane. Okay, so now we need the function, which is 2x plus y over 5. Okay, so we will have 2x, 2 something, plus y something over 5. And then we are going to multiply the whole thing by v. So v times this. Okay, so our x is 3 plus 4 cosine t. 3 plus 4 cosine t. I saw what happened. And we will have 2x plus y. So plus y is 2 plus 4 sine of t. Okay, and it seems to be unhappy right now. Of course, it doesn't have the times sign, so we have this. Okay, there we go. All right, so here is our curtain. Okay, so yeah, I decided to divide by 5 so that it looks a little bit nicer. Okay, so because if I have the full height, I think it's going to be too tall. See how that looks? Yeah, that's way too tall. So let's keep it at 5. Okay, and yes, there it is. Okay, so our goal is to find the area, the surface area of this curtain. If you roll it flat, okay, what will be its area? So notice we can hide the curve, yeah, and the floor on the xy plane is going to be the curve, which will be our domain. Okay, so let's continue now. We will take our function and we will plug in r of t. Okay, so we want f of r of t, 2x. So this is our x, 2 times x, plus y. Here is our y. Okay, and shall we just simplify? Yeah, there's some constants that'll go together. Compute, simplify. All right, there we go. So we also need our r prime. Okay, so take the derivative. R prime is going to be negative 4 sine t. and that's going to be 4 cosine t. Why do I erase that? I don't know why. Okay, and then we need the length. Okay, but yeah, so we can see it clearly, don't you think? So we got 16 sine squared, 16 cosine squared. That adds up to 16. Square root of 16 is equal to 4. Okay, another way to think about it is you have 4 times a unit vector, minus sine t, cosine t. That's a unit vector. Okay, so we are now ready to find the area of our curtain. So we have integral from 0 to pi over 2 of our function, which is this, and our 4, don't forget the 4 dt. Okay, a lot of times you work for something, oh, and then you forgot to include it. You just wasted 5 minutes of your time. Okay, so we can take our 4 outside. Oh, we can take 16 outside. Isn't that nice? So that will be in 16, and careful how much we take out. We'll take a 4 each, so 2/5 and 1/5 and 2/5. Yeah, dt. Okay, and now we can integrate, and we will get 2/5 of sine, right on, and then minus 1/5 cosine, minus 1/5 cosine of t, and 2/5 times t. Not there, inside. Okay, t is going from 0 to pi over 2. Okay, there we go. Ooh, yeah. Careful with that cosine. It's so annoying. When you plug in 0, you're going to get 1, not 0. Okay, so 1 at a time. Sine of pi over 2 is 1. Sine of 0 is 0. Cosine. Cosine pi over 2 is 0. Sine of 0, cosine of 0 is 1, so minus 1. And then 2/5 times pi over 2. Oh, how convenient. So that's pi over 5. Yeah. Okay. So you get 2/5 plus 1/5 makes 3/5. All right. So we got 3/5 plus pi/5. So yeah, if you want to make it look even nicer, we can make it 16/5 times 3 plus pi, or pi plus 3. Wouldn't that look better? All right, there we go. Okay, so that would be the area of the curtain that we just drew in GeoGebra, 19.65. Okay, that's realistic. Okay, so there we go. That's our introduction to contour integrals. In our next video, we're going to look at vector fields, and a little later on, how to integrate those vector fields. All right, so until then, I hope you enjoy the rest of your day. I'll see you at our next video. Bye-bye.